Hi, everyone. Thank you for coming for this seminar. At this year's summer school, I taught a deep learning course there, but I spent a little bit too much time on the principle of the neural network, how to train it, and I spent a little bit too much time on the backpropagation and all the math behind it. And then I didn't have a sufficient time to cover the second part, which is how to use a TensorFlow to tackle a deep learning problem. Today, I'm going to focus on using TensorFlow to solve a real-world application, which is recognition of handwritten digits. Okay, so let's start with some brief introduction of neural network. The neural network was inspired by discovery in the neuroscience. And basically, it is a graph of neurons, and each neuron takes multiple inputs and generates one output. I want to get your attention that it generates one output from each neuron. Okay, so on the graph left, you see, for example, you see a neuron in the hidden layer. It has two, for example, has two output. No, it's actually not. You have to have two arrows. It's just one output split to as an input for the next layer. Okay, so basically you have one input layer and one output layer. You can have multiple hidden layers. Okay, and now let's look at the neurons. So the most commonly neuron is linear weighted sum. Basically, you can consider if you want to make a claim or classification as that, you may collect a few evidence as input, as x1, x2 until xn, and each one you associate with a weight w1, w2, and wn. And what you are going to do is, because those evidence, some of them support the claim, some of them may reject the claim. So that's the weight could be positive or negative, or the absolute value of the weight represents the influence. Okay, so basically what you do is you use the weight time multiply with the input, and do it one by one, and then sum the products. So you got something like this. This is the math formula. I prefer to write it in the vector form. Okay, and after that, usually you want to see the weighted sum whether or not it's greater than a predefined threshold t, and if yes, you let the neuron fires. Otherwise, it's still keep inactive. So that's the basic idea. But in mathematical, if you reformat the formula on the left, on the left, you can get something like this one. It's equal, and now we have a new meaning for W and B. W are the weights, and B is the bias for the neuron. Another neuron is sigmoid. So once you got the weighted sum plus bias, you can instead of either go through the previous one is step function. Above 0 is 1, If it's less than 0, is 0. But now we have something like this. If it's above 0, it's a gradually increase and decrease. So this is a sigmoid function. And we can also use another function. It's called relo. Relo is rectified linear units. So it's quite similar to the previous one, but when it's less than 0, I mean the weighted sum plus files. If it's less than 0, we don't file at all. But if it's above 0, we file, and the magnitude depends on the z, on the weighted sum plus files. Okay. So that's the recognition file. So convolution layer is a very powerful tool in deep learning. You probably heard of this quite often. It's very useful in image recognition. Basically, you define a kernel, which is a small patch of image. It's a 2D array, actually. Smaller, most compared to the original image. It could be like 5 by 5 or 10 by 10 or something like that. The convolution operation is something once you put the kernel and you slide over the original image at any position, you do multiplication elements-wise. So that means for the kernel overlap with the image, you find the corresponding pixels. For every pair of pixels, you multiply them together, and then do the summation of those products. So that's the convolution operation. So once you slide the kernel over the image, for each step you do the convolution operation, you can get another image. And another is polling layer, which is sampling. So here I show max polling, which is you see for every 2 by 2 subregion, I choose the maximum. For this yellow, I choose 6 because 6 is the maximum. Green, in the green area, it's 8, and in the gray, it's 4, and this one blue is 3. So after polling, we got from the original 4 by 4, I got a 2 by 2. Okay, it's reduced by half. But certainly, you can, instead of 2 by 2, you can have a 3 by 3 or 4 by 4 max polling, and it's up to the application. And generally, this is the nowadays this is the architecture for image recognition. So basically, you do the convolution, then polling, rectilinear, and do another round of convolution and the polling, and then do the so-called fully connected layer. But you can have multiple of those, depending on the application and the performance you want to achieve. Now let's go to the second part. So we are going to take the recognition of handwritten digits as example to show you how to use the TensorFlow to solve this problem. So handwritten digits are shown something like this, just a few of the examples of handwritten digits. To do this, we need 4 elements. One is the training set or the data set. Secondly, you need to decide the architecture of the neural network you are going to use. But this is a tricky part because there is no clear guideline or something to say which architecture is the best. You have to, try and different one. But in general, you have to base on some previous successful example and try to, for example, either change the parameters or change the architecture by the number of layers or something, and then you could find the best solution. And after that, you need to define a cost function, and I will explain this part later on. The reason that we need to define a cost function is for training, because the whole purpose of training is to determine the parameters in the neural network. So we have to find a way to minimize that, a predefined object function or cost function. And the last part is what algorithm you are going to use. So there's a bunch of those. SGD is the most popular one. It's called a stochastic gradient descent, and there's some others. And I'm not going to talk about each of those methods, because basically today we are going to use TensorFlow, and we just call a function in the TensorFlow, and it will do the job, okay? And now let's look at the data set. The data set is from Yan LeCun, New York University. And the data set is quite popular, and it has 60,000 training samples and 10,000 testing samples. And each sample is a 28 by 28 grayscale image, and with a label telling you what digit it is. And the label could be 0 or 1 or 2 or until 9, any of those. And it vectorizes as a one-hot vector, which means I create a vector of length of 10. Only one of those elements is 1. For example, this one is a 0, 1, 2, 3. This means it represents the digit 3. Okay. Instead of label, I used the one-hot vector label. Okay. Now let's look at the data. So, like I said, it's a 28 by 28 array, and each of the element, the background is 0, 0, and the stroke, for example, this is I have a 1. You see the middle one is 1, and on the between is something is not that between 0 and 1, and the label is 0, 1. So this is 1. So that's the data set. Today I'm going to use the sample in the TensorFlow website, which is quite standard one. So I'm going to use the so-called deep learning for beginner examples. So let's take a quick look of TensorFlow. TensorFlow provide Python APIs. I think it provides C API as well, C+ API as well. But today I'm going to use the Python API. The API has 2 levels. One is quite low level, and the other is high level, which is more efficient than the low level. I'm not going to talk those in very detail. But today, the purpose is I go through a concrete example, and I leave you to explore the rest, because I only have 1 hour, actually 50 minutes. I try to limit this talk to 50 minutes. So Tensor is the central unit data structure. It's tensor is not basically it's just a multi-dimensional array. It could be one-dimensional, which is a vector, two-dimensional, three-dimensional, or four-dimensional. Image recognition, sometimes we use four-dimensional. The first dimension, the first dimension is the number of images. Second dimension is the height of the image, and the third is the width, and the last one is channel. Channels could be if for the original image, it could be red, blue, green channels, but in general, it could be more complex than that. Later on, if you after the convolution filter, it doesn't have very concrete meaning, but it's just a channel. Could be anything. TensorFlow has a concept called a session. Later on in the code, I will show that. It's the central control of the execution of the data flow. So I will show that later on. So when a user uses TensorFlow to tackle a deep learning problem, the first part is to specify the task, or to construct a computational graph or neural network. The second part is to run the graph, and the graph is a directed graph with edge connect nodes. So it's basically just like our neural network we defined before. Within the graph, there's a bunch of entities. One is constant, the other is variable, and the third one is very special. It's called a placeholder. It's reserved for input data. You have training data, but once you define the neural network, you haven't pulled in the input data, so you have to define a placeholder in the graph. Now let's tackle the recognition of handwritten digits problem. So I'm going to define very simple, fully connected neural network as shown here. And the input layer contains 784 neurons. Why 784? Because our image size of 28 by 28. So we have totally 784 pixels. So we vectorize the 2D array of image as a one long vector with a length of 784, and take them as an input for the neural network. And the output is a 10 element, each of which represent the likelihood of being digit 1, 0, 1, 2, and until 9. So the bigger number it output, the more likely it would that digit would be the output. For example, if the third output got the largest number, then I will consider number 2, because this is 0-bit. So number 2 is the output. So the image is actually contains a digit number 2. Okay. So because this is the fully connected, so basically all I do is for each node, output node, I time the weight with the input node and sum them together, and then plus a BIOS for that node. That's the input for that one. So that's basically a very simple one. Let's go to the next step. So now once we define the architecture of the neural network, the next step is how to train this neural network. What does training mean in this case? The training in this case is the purpose is determining the parameters of this neural network. What are the parameters? Let's go back. The W, which is the weight for each on each of the lines, there's a weight. So Wij is the weight from the ith node on the input node and connect to the node on the jth node on the output layer. So that's the weight, and the Bi is output node. Okay. So we have for this one, how many W we have? We have 784 times 10, which is 7,840 weights. And how many BIOS? B, 10. We have 10. We need to determine those. And determine those to make the output matches the ground truth, which is Y prime. Y prime is the label of the sample image. So X and Y prime are pair. So X is the 28 by 28 image. Y prime is the label, and we want to train those neural network to make the output of the neural network matches the true label. Okay, how to do this? This is something we need to define a loss function. There's so many ways to like the the mean square error, or here I'm going to use softmax cross entropy as the cost function. So basically, once you define a cost function, you want to minimize the cost function by choosing a better parameters, which is weight or and the BIOS. Okay. So how? This is the solver, which is for example, you can use a stochastic gradient descent solver or some other method, but we are not going to talk about this because we don't have time. All right. So what is a soft cross entropy? First, talk about the softmax. So let's say we have output from the neural network from Y1, Y2 until Yn. In our case, n is 10, and we squash those numbers into a range between 0 and 1, and make them sum to be 1. This means we turn the output into a probability distribution. How to do that? We take the exponential of each component, and we sum them together as the denominator, and that's it. So this is the formula. So this basically squash the original output. Could be very has a very large variation into a very into the range between 0 and 1 because it's a probability distribution. Once we achieve that, let's take a look at what is cross entropy. Cross entropy is from information theory. So suppose we have a prediction probability y and the true distribution of y prime over certain events or claims or predictions. For example, in this case, we have 10 events or claims. We say either an image is digit 0 or 1 or 3 until 9. So what we will do is for the entropy is this formula. So you will see that if because the true distribution is only one of them is 1, the rest of them is 0 because we use one hard label. So to make this cross entropy minimum, the y should be exactly the same as y prime, and the range for that one is 0, and otherwise it's a number, a positive number. Okay. So soft cross entropy is if we concatenate those two operations, which one is the first one is soft max, and then do the cross entropy, which is we put them together. We call them soft max cross entropy. If the input image is digit 2, I wish the third neuron in the output layer give the largest output. Okay, that's my hope. Okay, if I achieve that, and then later on I can predict correctly. So basically, I want the output match my desired hope. Okay. So how to do that? As long as the better it matches, for example, the rest of them are all 0, only one of them, the correct one, gives a big number. Okay, then I got a very good prediction. So this one will the soft max cross entropy will be minimal. Otherwise, it will be a larger number. So the task for the training is actually becomes a minimization problem. How to determine the parameters, which is W and B, to make the soft max cross entropy smaller and smaller. Okay. All right. Once we trained the neural network, we can use the trained model by simply pass an image to it, and then we got output 10 outputs here, and we choose one that has the maximum the largest value, and if output its index. This can achieved by argmax. Argmax is to find which one is the biggest. Suppose the fourth one is the biggest, then we output the index 3 as output as a prediction. Okay. All right. So let's take a look at the code. First of all, we log in to okay. So this is the code. But first, let's see project 1. Okay, first we go here. We have data, which is the data, those 4 of them. download from Yan LeCun's website. Okay, and the source code is here, which is Python code to run TensorFlow. I installed it under my local directory. It's under my home directory .local, and to run it, I need to set it up. So first, look at this one. Oh, sorry. And basically, I need to load Python because Python 3.5. I want to use GPUs. I load CUDA and CUDN modules. Then all I need to set up the environment variable like lib and also path, etc. The TensorFlow bin is in this my home directory under the local bin. So later on, I'm going to write a wiki page about how to set up TensorFlow. But if you have question, you can contact me right now after this seminar. Okay. So basically, I just TensorFlow and source this one. I make the TensorFlow ready. I'm going to run this one. This is the source code. I'm going to show this one. How to submit a job. Let's look at this one, TensorFlow job. I create a bash. Basically, you define the time. I'm asking for 20 minutes. I think it only runs like less than 5 minutes. But I'm to be safe, I ask for 20 minutes. This is the name. The output is here. And append the job ID. I'm asking for 5 GB memory, and I only ask for 1 GPU. And I'm only going to run this Python. This is the the application. So okay. So I'm going to submit the job. Go. There's an error there, but I will fix those errors later on. But it doesn't affect the performance. So I still got it. Still works. So the job ID is this one. That's Q. My name, my username. You see, it's running. And if I do list, you'll see I already got some output. You will see this is the job ID appended here. So this output, but it's not finished. I can tell from the size of the file. Again, okay. So I don't think it even finished the loading the data, but it's not. But never mind. We take the time to study the code line by line. All right. So here, this is the code. First, I input the. There's a module about how to loading the MNIST dataset, which is the handwritten digital dataset, and I input it. And second, I import the TensorFlow. And now I'm going to input the data. So basically, the object is MNIST. After it contains all the data, both the training and the testing. Okay. So this is what I'm going to do. I specify where the data is. Okay, I'm asking the label to be one hot vector. Okay. Now look at the code. The first part, X, is the image. Okay, you know, I make it like a placeholder because I don't know how many images I have in the training data. Okay, so I make the first dimension loose. I put it none there because I don't know how many images there. But actually later on it's 60,000. But right now I don't know. Okay, and because it's 28 by 28, altogether I have 784 pixels. So this one, and like I said, the second one is the weight. Because I know the size, so it's 784 by 10, and I put them all 0. And third one, I create a BIOS, which is also a variable. And finally, I do the multiplication. You know, what I do is this matrix multiply, so x times w, this is what I get. And that's just the formula that if I go back, this formula, so it's a multiply then plus b. Just this one sentence solve this formula, okay? And probably you'll wonder, because TensorFlow has a different philosophy about programming in Python. You know, the x is not determined yet. It's hanging there because we don't know the data. We don't even know the first dimension. How could you multiply? I said, right now, I'm defining the neural network. I will do a matrix multiply with a vector, but I haven't. But it's just a definition. It's not being executed yet. I will show later on it will be executed. Now I just define the operations in the graph. Okay. Second one, which is you see y underscore is a placeholder for the label. I define the label because I don't know how many images. So the first dimension is none. Okay. Now I'm going to define the cost function. I call it a cost entropy. And basically, you see, I just use one of them to do the trick. So basically, for each one is y underscore, the other is y. So y is the output. Y underscore is the true label. So I want to calculate the softmax cross-react speed between those two. Here, the y and the y underscore are two-dimensional. The first dimensional are the numbers of the image. The second dimensional is 10 because it's a one hot vector. Okay. So I'm going to do the calculation. After the calculation, I got a two-dimensional array. Okay. The first dimension is the number of images. The second dimension is the softmax cross entropy. Okay, which is a value. Each of them is a value between 0 and 1. But I don't care. But I want to make I want the whole thing because I want to sum up all the losses that is calculated from each pair, each images, and then divided by the number of the images to get the mean. So I can do that just by calling mean and take that as take those cost entropy as pass those as a parameter into this function. Okay, just those simple. So now I have defined the cost function. Now I'm ready to define how can I change the W and the B, the parameters, in each iteration, I mean each step. So I define a train. I'm going to use a gradient descent, okay? And the parameter is the learning rate. So learning rate is something, is a quantity to control the steps. If you should be careful, because if it's too small, it converges very slowly. But if it's too large, it may become numerically unstable. So here I choose 1.5, and I choose the cross entropy that I defined in the previous statement as a target. I'm going to minimize those ones. Right now, nothing has been executed. It's all definition. So now, from now on, I'm defining a session, and I'm going to initialize the variables, global variables. And last two things I'm going to define. Define the prediction, because later on I'm going to check the accuracy of the prediction using the testing data. Okay. What I'm going to do is, you see, I'm going to see if this is the output argmax. So y is the output from my neural network. I'm going to see which one is the biggest one. This one output the index, which is tells us which digit it is, and this one is telling us which one is the true label. And then I try to measure whether or not these two equals. So it's give us a big array of true and false. Okay, depend on how many images in each of those. Once we got those, we cast the Boolean into float. So we got a lot of 1 and zeros, depend on whether or not it's true or false. So it is a large one-dimensional vector. Each element is either 1 or 0. 1 means correct prediction, 0 means wrong. Okay. So then we do the mean. Actually, mean is the percentage of accuracy, how many images are correctly classified, okay, predicted. All right. So now I'm ready to run the training. Like I said, so up to this point, nothing has been executed. So we are going to go through the loop. So first, the strategy for training here is, I'm not going to use all the training data, because 60,000 images, it's going to take a long time. So a good strategy is I'm going to divide it into a lot of batches. Each batch contains here 3,000. So I'm training going to loop those. So every time I'm going to ask MNIST to give me the next batch, next 300 samples. So it will loop, so give those X, this X, and Y's. X is the image, Y is the true label. So I'm going to run now. So I'm going to run, so this is the interesting statement, just one statement. I'm going to run on the training step defined before, okay? I'm going to replace the placeholder in previous design, which is X and Y underscore with the training data. One is image, the other is label. I just do a one round using the 300 samples. And over and over, then use the next 300, then use the next 300 samples. I'll loop. I will loop so many times. And I'm not going to output for every iteration. I'm going to output every 100 iterations. So for every 100 iteration, I will calculate the accuracy defined here using what? Using the test image instead of training images. So test image here is only contains 10,000. Okay, so use this one replace X. Using this one replace Y underscore in the previous definition. Okay, so that's it. So let's see. Because we already submitted the job, I think it will finish now. Let's check. Okay, nothing there. I assume it's finished. Let's see. Okay, this is the output. You see the time. Today is July 5th. It finished like 10 minutes ago. Let's look at the output. Okay. The previous one is the TensorFlow related. So from here, it loaded the data, and now I see the output of the accuracy. Those are the outputs from the iteration, from every 100 iteration. So first I see, okay, the performance is not very good. About the 38% of the images are correctly classified or predicted. And then I got 85% and 90%, and gradually I got, around 92%. Okay. The other one, yeah, we don't have time. But once you understand this, it's not very hard for you to go to the next one, which is use a convolutional network, which is much more powerful. With that one, you can get the prediction accuracy over a little bit over 99%. I'm going to stop here.